All right. So, greetings, YouTube. Beautiful Mind here. We have this question from. So, this is a calculus course, but I want to say that this concept comes from college algebra. Not that that makes it any easier. To be honest, I feel like calculus is easier than pre-cal. Not necessarily easier than college algebra, but I feel like calculus is definitely easier than pre-cal. And some of these questions are definitely pre-cal. But nonetheless, so we have this question, a calculus question based on college algebra. Let's read it. So it says, if f of x equals the greatest integer less than or equal to x plus the greatest integer less than or equal to negative x, show that the limit as x approaches 2 of f of x exists, but is not equal to f of 2. All right. So I feel like there's some components of this that we need to discuss. So this symbol, it's called the greatest integer function, this guy here, right? And let's work a few examples. I feel like the best way to kind of grasp that concept is to see a few examples. So for instance, whenever we have the greatest integer, we want the greatest integer less than or equal to our x value. So whenever we get a number in that double bracket thing, if you think about that number on the number line, you always take the integer to the left. If you have an integer in there, then just take the integer. So the integers are basically your positive and negative counting numbers. So integers are like 0, 1, -1, 2, -2, 3, -3, so on and so on and so on. So whenever we have an integer, you just take that number, right? But whenever you get like a fraction or a decimal between two integers, you always take the integer to the left, right? So let's do a few examples. So for instance, if we wanted the greatest integer less than or equal to, say, let's do 2.5, right? If this were on the number line, 2.5 is between 2 and 3. So the integer to the left on the number line is going to be 2, right? What if we wanted the greatest integer less than or equal to 2.9? Again, that's between 2 and 3. The integer to the left is 2. Well, what if we wanted the greatest integer between, let's go 2.1, right? That one's also 2. What if we wanted 2.01? That's 2. What if we did whole bunch of ones like this, a whole bunch of zeros and then a 1? That's still 2, right? Suppose we did the greatest integer less than or equal to 2 itself. Again, whenever you get an integer, you just take that integer. So then if we did the greatest integer, let's do 1.9. Now 1.9 is between what? 1 and 2. So the greatest integer less than or equal to 1.9 is going to be 1. Right? If we did 1.5, that's also 1. If we did 1.1, that's also 1, right? So on and so on, right? So again, whenever we get a decimal or a fraction between two integers, we just take the integer to the left on the number line. If we get an integer, we take that integer. I need to do a couple of more examples. So suppose we considered negative 3.5, right? What's the greatest integer less than or equal to negative 3.5? This is a good opportunity to pause the video and see if you can get that one correct before I submit it. All right, so hopefully you've paused it. Let's see. So now, if we were to look at negative 3.5 on the number line, it's between what two numbers? It's between -4 and -3. So what's the integer to the left on the number line? This one is -4. All right. If we did the greatest integer less than or equal to -3.9, that's also -4. If we did -3.1, that's also -4. If we did -3.001, that's also -4. If we did the greatest integer less than or equal to -3, again, that's an integer, that's just going to be -3. All right. So the main takeaway with this symbol called the greatest integer function, whatever number we get that's in those brackets, we imagine that number on the number line and say, okay, it's between what two integers? What's the integer to the left? What's the integer to the right? We take the integer to the left. All right. If it falls exactly on an integer, then we just take the integer itself. Okay, so that's the greatest integer function. That's the greatest integer function. So we needed to talk about that symbol. Okay. So then I think I might just copy this. Copy. Let's add a page. And we can go ahead and paste it here. Okay. Oh no, undo. Okay, that's fine. Paste. Okay. All right. So let's go back. Sorry. Okay. So we did an introduction for the greatest integer function. We're asked to show that this limit exists but is not equal to f of 2. So now let me label this. Again, this is called the greatest integer function. And that's referring to this symbol. And the graph of the greatest integer function is called a step function because it's going to look like the stairs on a staircase, the steps on a staircase. All right. So if you were to look at this graph, this one's kind of hard to visualize in like a graphing calculator because it doesn't, the vertical lines, it keeps trying to connect them and it's not supposed to. It's supposed to be a whole bunch of gaps. But the graph, it looks like the steps on a staircase. All right. So this is called a step function. Okay. So then with limits, right? So from last time, let me mention this. So when it comes to limits, in order for a limit to exist, the limit from the left has to exist, the limit from the right has to exist, and those two have to equal each other. So we can say, we can kind of articulate that like by saying the limit as x approaches a from the left has to equal some number. The limit as x approaches a from the right has to equal that same number. Then when this is the case, then we can say that the limit as x approaches a of f of x equals L. Okay. Let me create a little bit of space here. A little bit of space here. It needs to be a f of x there, f of x there. All right. So again, limits are concerned with how is the function behaving as we get really, really close to this x value coming from the left and as we come from the right. Okay. Now, in subsequent sections, there's an extension to this. When the limit from the left equals the limit from the right equals the value at the point, then that's the definition of a function being continuous. But if it's not, sometimes it's not necessarily equal at that point, then it's not going to be continuous. It's going to show up as either a hole or a gap in the graph or like, something along those lines. Okay. All right. So given this function, we want to show that the limit as x approaches 2 of this function exists. Okay. So for instance, let's evaluate. Let me think. So when x is 2, the first one is what? 2. And the second one looks like it's negative 2. Because usually when you have an integer in the brackets, you just take the integer. So it looks like it would be 0. All right. So then what would this graph look like? Why wouldn't it just be 0 across the whole thing? As x approaches 2. Okay. No. Give me just a moment. I'm trying to think of something. So if we put a 2 there, coming from the left of that guy, but why is it not necessarily equal to f of 2? Okay. So one way that we can show that the limit as x approaches 2, we can isolate the left and the right. So like if we consider coming from the left, right? So another way to kind of do limits that we haven't talked about, we can explore it coming from the left and coming from the right. I need another page. And so let me show you what I mean by that. Can I just paste? That would be nice if I could just paste. Okay. Let me get rid of this. I can get rid of all of this. Okay. So now, if we want to show, let's start with the limit. Let me clean this up. The limit as x approaches 2, we want to consider it coming from the left of this function, right? So we can do this with the table. Like, let me see. So if we consider it like x versus f of x. Uh-oh, is my pen? No. Oh no. Oh shoot, and there goes my mic. I gotta charge my pen. All right, so let me kind of talk through this. My pen just died. I got to charge it for a few seconds. So again, one way to conceptualize limits is by making a table. So the x value in question is when x is equal to 2, right? Or as we approach 2 from the left and the right. So we're going to start by considering the points as we approach 2 coming from the left, right? So I did that superscript of the minus. That means as we approach 2 coming from the left. Okay. So then here we're going to have f of x. So now coming from the left, right? So we might start with, like when x is 1.5, find the corresponding y. And then when x is, because it's a step function, it's going to kind of, I see it now. I think it's coming together. When x is 1.5, and then when x is 1.9, and then when x is 1.99, right? See, notice these x values are getting closer and closer and closer to 2, right? And we're going to have things that happen, right? So now we can use our calculator here. If we were going to do this in the calculator, we would use what's called a floor function. But I think I'm going to just do this one manually, all right? So let's first consider f of 1.5. Yeah, let's just do it manually. I feel like that'll be a little bit better. So now, that means what we're going to have is the greatest integer less than or equal to 1.5, right? Plus greatest integer less than or equal to a negative 1.5. Okay? So let's see what happens when we do this. That first term, 1.5 is what? Between 1 and 2. So the integer to the left, that's going to be a 1. Okay? Negative 1.5 is what? Between negative 2 and negative 1. The integer to the left is going to be negative 2. So 1 plus negative 2, that's going to add up to negative 1, right? So this output here should be negative 1. It's probably going to oscillate between, I'm imagining negative 1 and 0, but let's keep going, all right? So that was f of 1.5. Let's do f of 1.9. Now, I would imagine it would be similar. f of 1.9, greatest integer 1.9, greatest integer negative 1.9. Okay, 1.9, the integer to the left is a 1. Negative 1.9, integer to the left is a negative 2. So that's the same thing, right? Negative 1, right? So it looks like all of these should behave in a similar fashion. So coming from the left, it looks like this function is approaching negative 1, right? And you can make an argument. Once you get the first few, then the pattern should repeat for all those values coming from the left, right? So as x approaches 2 from the left, our y value is pretty much staying constant at negative 1. Let's evaluate this guy as x approaches 2 coming from the right. This guy right here, that's what I need. I need it from here. Actually, yeah. Copy. Guess I need another page. And let's paste. Okay. So now now we want to evaluate it as x approaches 2 coming from the right. Okay. So then we're going to make our table. We're going to have our x versus our f of x. Okay. Now coming from the right, these are going to be numbers like when x is 2.5, when x is 2.1, when x is 2.01, x is 2.001, and we could keep going if we wanted to, right? Let's find the corresponding y's. So first, let's evaluate f of 2.5, right? So if we plug it into that first part, the greatest integer here, let's just write it. Let me not be lazy. 2.5 plus the greatest integer less than or equal to negative 2.5. I have to bear with my handwriting. Okay. So now for that first term, 2.5 is between what? 2 and 3. So the integer to the left is going to be a 2. Negative 2.5 is between negative what? Negative 3 and negative 2. So the integer to the left is going to be a negative 3. Same result, negative 1, right? Okay. So that suggests that the pattern for all of these guys is also going to be negative 1, right? So that brings it on home. That gives us what we need, right? So if we go back, let me see if I can find it. Okay. Let's go back a little bit more. A clean one would be nice. Hopefully I can still paste. Matter of fact, let me just go here. I'll just use this. Paste. Nope. Undo. So now I gotta find a copy. Sorry. There it is. All right. Copy. So now we can bring it all together. We got what we need. Paste. Okay. So okay. All right. So again, given this function, we want to show that the limit exists. Again, just a moment ago when we started, we said in order for the limit to exist, the limit as x approaches some number from the left equals something. The limit as x approaches a from the right equals that same number. And so for the limit to exist, the left-hand limit has to equal the right-hand limit, which is exactly what we got. But if we plug in 2, I think we get 0, right? So through the table, we showed that as x approaches 2 from the left, we got negative 1. As x approaches 2 from the right, we got negative 1, right? So let me write it out. Oh, my pen keeps dying. Oh. All right. So I'm gonna let that charge for a moment. But yeah. So this one's pretty much done. So again, for the limit to exist, we just showed with the tables, the limit as x approaches 2 from the left equals negative 1. The limit as x approaches 2 from the right equals negative 1. So then we can say that the limit as x approaches 2 equals negative 1, right? But when we evaluate, when we just plug in 2, I think we're going to get 0, right? But that's exactly what we expected here. That's exactly what we want, right? Right? Okay. All right. Give me just a moment. Okay. So again, from the table, we showed that the limit as x approaches 2 from the left of this function, we got negative 1. Again, from the table. And if you need a PDF copy of the stuff that I'm writing, just let me know and I can make it available. Also from the table, these are both from the table. The limit as x approaches 2 from the right of this function, also we got negative 1, right? So because the left-hand limit equals the right-hand limit, we can say the limit as x approaches 2 equals negative 1. But, and that's a big but, all right? Let's evaluate f Sorry. Let's evaluate this function. Let's evaluate f of 2, right? So that's going to be what? The greatest integer less than or equal to 2 plus the greatest integer less than or equal to negative 2. I think that's the function. Yeah, right? Okay. So again, we said whenever it's an integer, we take the integer. So then this is going to be 2 plus negative 2, which is 0. Right? Ugh, I keep forgetting to add pages. Let me just add a page. Go here. And I'll cut this. Do one other thing. I know it's a little bit. I didn't intend for it to be so all over the place. Okay. All right. Okay. So we were successfully able to show that the limit as x approaches 2 of this function, we got a result of -1, but f of 2, when we evaluate this function when x is 2, we got 0. Okay. And that happens. Like that's happens. But I think those are the main components. Now, how you submit that, that's the concept behind it as to why that outcome is the way it is. I think there might be some. Let me kind of glance at that photo real quick. Right here. So given this function, show that the limit exists, but it's not equal to f of 2. So the graph of this function is the same as the graph of g of x equals -1, which is essentially what we got. Everything, like all the decimals and fractions, essentially it collapsed to -1. Let me see when x is, if x is 1. But it seems like at the integers, we get a value of 0. With holes at each integer, right? So it's basically going to be a flat horizontal line, but there's a whole bunch of gaps. There's going to be a hole at each integer, and then each integer is going to have a value of 0. And the rest of the function is going to be a flat horizontal line between each integer of -1. Okay. So then I think you got the first part. The limit as x approaches 2 from the left. And again, so remember that result, that -1, we got that from a table. If we're approaching 2 from the left, we did numbers like 1.5. We got, the integer to the left was -1. When we did 1.9, 1.99, 1.999. If you wanted to do this this was a little bit more challenging to do in a calculator. Let me pull up my calculator. It's going to be here. Okay. Let's reload and refresh. Okay, so what we need is the floor function. Let me see. Ceiling and floor. I'm not 100% sure where that is. I'd have to research it a little bit. So that's why I felt like the doing that one by hand might be a little bit easier once you get the concept. Let's see, calculate here. Yeah, I had to. I know where's the other one. So I'll save that for another time. But where it says here, this one, the limit as x approaches 2. Let me read it off. The limit as x approaches 2 from the left. Again, that was from the table. We got a result of -1. The limit as x approaches 2 from the right. That was from the second table. We also got -1. So because the left-hand limit equals the right-hand limit, that's where this limit, we can just say the limit itself equals -1, right? For a limit to exist, the left-hand limit has to equal the right-hand limit, okay? And then we saw where when we evaluated, this was going to be a 2 plus -2. So that was going to be a 2. This was going to be a -2. And then we got a result of 0. All right. There's going to be a -2 there and a 0 there. because that comes out of the concept of the greatest integer function, right? Like we talked about below. Okay, so I know that was a little bit long-winded, but I did my best to try to fill in like the necessary components. Okay, so I'll forward this to my student, and if anything isn't clear, we can kind of like do a live chat back and forth on anything that's not clear. And so with that, we're going to end the session here, and momentarily I'm going to kind of get this one started as far as processing, and then I'll get started on another question. One of those questions I feel like we need to do live because I need to see their responses. But yeah, so like I said, I'll go ahead and get started on another. So with that, we'll end the session here, and from one beautiful mind to another, take care. Peace.